Şuna 지랄이야.
Lan. 왜? 뭐?
Hello, everyone. Welcome back. I actually went to the wrong Zoom meeting for 1 minute, and there was a student in that Zoom meeting. It was really funny. I hope the student figured out that was the wrong one. All right, so where should we start? Let me share my screen. Okay, so we were somewhere here. We were talking about min hash. I hope you still remember. So our goal for generating min hash functions is to do what? Anybody? Okay. So this week last week we were looking at algorithms to help us compare documents and find similar documents, right? And we talk about this concept called shingles. And we say we can use shingles to represent documents. So each document was a really long string, but now we can use a set of shingles to represent a document. If you don't like shingles, think about all these items all these baskets that you can use items to represent, right? The same thing. So now each document is a set of shingles, and we want to be able to compare many documents to find similar documents. And we cover this Jacquard similarity idea. We say, hey, Jacquard similarity is very good in comparing two sets. However, the challenge here is the sets are really large. So if you look at the characteristic metrics, now you have 1, 2, 3, 4 documents, and each document can contain some of the items here. And what are these items? What is 0, 1, 2, 3, 4? Well, these are just different types of shingles or different types of items that you can have for each of the documents, right? So 1, this is important. 1 means S1 contains 0, 0 means S1 does not contain 1, and so on, okay? And we talk about this min hash idea. It's really cool if we go back to look at this. This is the takeaway for your min hash functions. Our goal is to be able to find a hash function. For that hash function, we will say if we use the hash function to hash document I and use the same hash function to hash document J, the probability of their signature being the same would equal to their Jacquard similarity. So this is pretty cool. And we show you that's the case by using these X and Y zeros. And now we are here, okay? So now we are saying that, hey, we can do this signature, but it just means we are going to look at this characteristic metrics, and we're going to scan from the top, and we will say every time when we see a 1, this is your signature. So for S1, the signature would be 0. For S2, the signature would be 2. And for S3, the signature would be 1. For S4, the signature would be 0. And you can easily see that the signature of a document depends on the permutation of the rows, right? If I change the order of all these rows, would S1 have a different signature? If I randomly permutate the row IDs and I still scan from the top?
Probably.
Maybe, right? We don't really know. because we say randomly. So if you look at this, we are saying that, hey, let's just take this characteristic matrix. We look at the row, we generate a signature, then we permutate the row again, we generate another signature. So in this case, we are taking a really large dimensions. Could be thousands of items because your dimension depends on how many rows you have here, into very small dimension. Okay, so now you have H1 and H2, you only have signatures, two signatures, and you use two signatures to represent a document instead of using 1, 2, 3, 4, 5 dimensions. Are we good so far? So the way to generate all the signatures is you can, well, I think in the textbook and also on the slides will tell you that you first permutate this row ID, but you don't have to permutate it for the first time as well, because if you assume the row numbers are randomized in the beginning, you can say, all right, let's just take 0, 1, 2, 3, 4, we generate a signature, and let's permutate it again, we generate another signature, and you're done. But how do we do this? So it's really costly to permute millions of rows, right? Yeah, that means you're going to take all these numbers and you're going to shuffle them in some way, and you're going to process this large table to do the shuffling. Well, we say large because in reality, you can have millions of documents and you can have millions of rows here. So if we don't want to touch this, what we can do is we just permutate the row IDs. So this is the original row ID, and let's create a hash function. This hash function is very cool, right? So it's mod5, and this one is also mod5. That means your result can only be between 0 to 4, well, including 0 and 4. So how do we generate 1? We say 0 is the input, 0 plus 1 mod 5 is 1, 1 plus 1 mod 5 is 2, and so on. So basically, you just push the row ID, you just increment the row ID by 1. And if you are at 4, it just becomes 0. Okay, so now you just permutate the row ID. So you only have to deal with one column. Then you do the same thing again for a second time, but this time you choose an independent column permutation function, and you have another set of row IDs. Okay, so pretty cool. Now we do not touch this table, we just permutate the columns. But how do we use all these 3 columns to generate min hash signatures? Oh, let's look at the result first. Say this is your original table, you have your new row ID, you have your old row ID, and you have a hash function to help you generate this new one from the old one. You still do not touch the table. You can use your new numbers to generate the hash values or the min hash signatures. Let's verify it. So S1, if we look at S1, you scan from the top, 0, 1, so okay, it's 1. S2, we scan from the top, 0, 1, 2, 3, so it's 3, and so on. Okay. So this one is pretty easy because the new row ID is 0, 1, 2, 3, 4. That means you always scan from the top. If you are not sure what I'm talking about here, let's look at the next example, and it will be clear here. So how do we do this? You have a table with all the documents, right? Now you have 4 documents, you have some row IDs, and you want to generate 2 signatures, okay? So assuming that you do not want to use original row ID. Let's say maybe the original row ID has some dependency, maybe the first 50% are from California, or transactions from California, the last 50% are transactions from somewhere else. So you don't really want to use it. You want to randomize it, which is okay. So you generate 2 hash functions. You say, let's use these 2 new row IDs to generate hash functions. to generate min hash signatures. So two hash functions give you two min hash signatures. So if you look at the result here, let's just look at the result really quickly. Your S1 now becomes two signatures, okay? One from H1, the other one from H2. All right, so how do we do this? Our goal is to scan the entire table once and generate both signatures at the same time. So we create this table first, the signature table. Because we already know we're going to have two signatures. The dimension will be 2 by 4 because you still have 4 documents. And you initialize this matrix into a really large number, okay, infinity here. So why do we want to do that? Remember, when you scan from the top row, when you look at row ID, you always are looking for the row ID with the smallest number that has a 1, right? Because you are scanning from the top. You start from ID 0. Okay. All right. Just assume that we initialize the table with everything using a large number. Then let's scan from the top. So let's scan this first row in the table. So remember, the min hash signature only cares about ones, not zeros, right? So S2 has 0, S3 has 0. We don't care about them. So S1 has a 1 and S4 has a 1. Let's look at the shuffled row IDs. Shuffled row ID tells you that for hash function number 1, you see a 1. Okay, you see a 1 for S1 at row ID 1. Great. So you just make a note here. 1. Shuffled row ID number 2 says 4. Document number 1, you see a 1 at location 1. So you put a 1 here. Okay, so why can we put a 1 here? Remember, when you initialize this matrix, it was a really large number, right? So now you have a small number. It's smaller than the really large number, so you can use the small number to replace it. Let's look at the second row. Now you are scanning the second row. Oh, sorry, you have S4. So S4, we see a 1 at a location 1. So you put a 1 here. S4, we see a 1 at a location 1 for hash function 2 as well. So you put a 1 here. Great. All right, second row. Second row, 0, 0, 1, 0. What does it mean? Well, you don't care about 0, no 0, no 0. S3 has a 1. So for S3, we saw a 1 at location 2 for hash function 1, and at location 4 for hash function number 4, right? So let's look at S3. S3, before we scan this new row, it has infinity and infinity. So now we saw a 1 at 2, smaller number than infinity, we just put 2 here. 4, smaller number than infinity, we just put 4 here. Great, we're done. So we're done for this 2. Now your next row, 0, we don't care. 0, we don't care. All right, S1, we see a 1 at location 3 and 2. All right, let's look at S2. S2, originally, before we read that row, has infinity, so we know we need to put 3 and 2 here, right? Because they are smaller than infinity. S4 becomes interesting as you see S4, we saw a 1 at row 3 and row 2. Let's look at S4. S4, originally, we say we already saw a 1 at row ID 1 and 1, right? Now we saw a 1 for S4 again at row ID 3 and 2. Do we want to update it? We do not want to update it because 1 is before 3 and 1 is before 3 and 2, right? Think about if you scan from the top, because this time we do not permutate the entire matrix, we only permutate the row IDs. So sometimes you will see a 1 before you see 2, or sometimes you see a 1 at location 1 before you see a 1 at location 0. It doesn't really matter. But the most important part is, let me repeat this again. This means for S4, document number 4, we saw a 1 at location 1 for hash function 1. We saw a 1 at location 1 at hash function for hash function number 2. Now, when we scan this row, we saw a 1 for S4 again at location 3 and 2. And since 3 and 2 are later than 1 and 1, so we do not update the value. Okay, so we're good. All right, next one, 1, 0, 1, 1. We don't care about 0, but for 1, S1, let's look at this. For document number 1, we saw a 1 at location 4 and 0. All right, so where was the ones for S1? We saw a 1 at 1 and 1. Now we say we saw another 1 at 4 and 0. Okay, so this 1 is smaller or before 4, so we keep it. This 1 is later than 0, so we have to update it. This 1 becomes 0. Great. So we don't care about S2, S3, and S4. So for 0, let's see, we have 4, 0, and 4, 0. You can easily see that this 2 is before 4, 1 is before 4, so we keep them. But both 4 and 1 are after zeros, so we have to update them. Okay. Now the last row, 0, 0, 1, 0. Let's look at S3. You have 0 and 3. It means now we have 0 and 3. Okay, 2 is after 0, so we definitely have to update 2 to 0, and we keep 0 the same because 0 is before 3. And we're done. So the really nice thing about this is we actually permutate all the rows without doing anything on this matrix. And we can generate whatever numbers of signatures you like by scanning the entire matrix once. Of course, you have to add new columns for the permutated row IDs, but it's very efficient. Okay, so this way you scan the entire table once, you generate 2 min hash signatures. Let's look at how the signature works. This is important. People are usually get confused about how to compute their actual similarity and the estimated similarity. This will be in your exam, so make sure you understand this. All right, so how do we compare S1 and S2? Actual similarity. What's the similarity measurement we are using? These are 2 sets, so we're going to use Jacquard similarity, and their intersection is what? 0. All right, so 0. Let's look at S1 and S3. What's their intersection? S1 and S3. How many
1.
items? All right, so someone says 1, so 1. Awesome. And what's the union? 1, 2, 3, 4. Okay, great. S1, S4. S1, S4 intersection.
2.
1, 2. Do we count 0?
No.
Why don't we count 0? S1 and S4.
Because neither set has that item.
Great. So this 0 does not mean it's character 0 or string 0. It just tells you that S1 does not have 1, S4 does not have 1. Okay, so your intersection is only this 1 and this 1, so 2. And your union, 1, 2, 3, so 2 over 3. How about the estimated similarity? If you compare S1 and S2, well, 1 and 3, not the same. 0 and 2, not the same. 0. How about S1 and S3? 1 and 0, not the same. 0 and 0, they are the same, so it's 1/2. All right, so now we are counting zeros. Why? Why is S1, S3 has an estimated similarity of 1/2? Shouldn't we just ignore zeros? Because we did not count zeros for here, right?
Because 0 is a position.
Okay, great. Because 0 is actually a position, it's a character in a long string. So if you think about this, S1 is now a string of 2 characters, 1 and 0, right? So to compare the similarity between S1 and S3, you just see how many characters are matched. So you don't use Jaccard similarity anymore. Okay, S1 and S4, the similarity will be 100% because you have 1, 0, 1, 0. All right, so if we do this for everybody, are these 2 numbers similar? Well, they are not exactly similar, right? What could be the problem?
Too small of a
Problem-
sample size.
Yeah, the data is just too small. So first, yes, not enough hash functions. But if you look at our example, we only have five rows. How many hash functions do you need? If you have 5 hash functions, that will be the same dimension as your original data. So this min hash only works, you only need them when you have really large data, right? Let's say you have thousands of millions of rows, and you probably use hundreds of signatures to estimate it. Then it makes sense. For this, it doesn't really make sense, but it's a really nice example to play with. All right, so the challenge, it's still large numbers of comparisons, and we have reduced large sets into small signatures, but we still have large numbers of pairs to compare, right? Remember this table. Now I'm doing this S1 here, S2 here, S3, and so on, and your columns are your feature vectors. Now we are saying that for min hash functions, we can make this smaller and use some min hash signatures to represent them. But still, you have a lot of documents, and let's say 1 million documents have a trillion pairs, right? Because you want to compare pairwise similarity. That will be C, 1 million, choose 2, that would be 1 million squared divided by 2. For 1 million documents, needs 6 days to compute similarity. So this is not going to work. Our next algorithm is going to help you with this. Next algorithm is very simple. It's called locality sensitive hashing. So LSH. The general idea is we want to be able to hash it again, but this time we want to hash the signatures. So if 2 signatures are similar, they should be in the same buckets with high probability, right? So something like this. Then we only want to estimate similarity for sets in the same buckets because very often we only want to find the most similar ones or a similarity higher than say 80% of the threshold, right? So you don't care about items in other buckets. For example, let's say I have many buckets. I'm just making this up. And I have all these documents, many documents in each bucket, okay? And I have a new document, and the goal is to find all the documents in all the buckets that has 80% or more similarity to this, okay? And the easiest way is just to compare these documents to all the documents here, every bucket, and that'll take a lot of time. But our LSH idea would be able to say, all right, let's rearrange all these buckets so that one of the buckets will have high probability to have all the documents that have a similarity to these new documents, and the similarity will be larger than 80%, so that you don't have to care about all other packets. Okay, so how do we do this? So this is very similar to this frequent bucket idea in the PCY algorithm. If an item pair not hashed into frequent buckets, we know it's not frequent. If this document and some other documents are not hashed into this same buckets, we know that we don't have to compare them. So let's define similar signatures. We look at the way to generate signature similarity from the last slides, but let's look at in what way they would be similar. So two sets are similar if there's a Jaccard similarity is larger than a threshold. If two sets are similar, their signatures should be similar too, right? That's by definition how we use min hash to generate signature. But what do we mean by similar signatures? Well, if you look at this table and ask yourself which two signatures are similar, we will say S1 and S3 are similar because they have the same value at many places, right? All these red places. Cool. What does it mean then? Well, this means we can generalize, we can have a general statement about signature similarity. We say two signatures are similar if they have the same value at many rows. So if a similarity of two sets is 0.8, then 80% of the rows in their signature should have the same value. We are going to show you this data, okay? But general idea is very simple. Many locations in the signature should be the same. So two sets are similar. If we look at sets, two sets are similar if they have the same value or if they have the same ones at many rows of the characteristic matrix. So if you have 0 and 0, you don't care. You can ignore them. If you have 1 and 1 at the same places, we care about them, but we don't care about zeros, right? These are for sets. But signatures are not sets. They're just strings of symbols, and signatures of sets are strings of the same length, something like this. So we cannot really use min hash like we did before, because if you permutate it and you scan from the top and you always get all these different values from each string, it's not going to work. And because we cannot really prove, okay, why is min hash signatures? Why can't we use min hash signatures on strings? Anybody? What's the most important criteria of the min hash signature algorithm we covered so far? Is the probability of two signatures being the same equal to what?
Jaccard similarity.
The Jaccard similarity between S1 and S2, okay? And if you look at this definition, this is the core of our min hash signature algorithm. If you look at this, can this apply to strings? Well, it can't, because this Jaccard similarity applies on sets, not strings, right? And now your signatures are strings, so this property will not hold, and you cannot use min hash signature this way. But just to be clear, there are other ways to generate min hash signatures without Jaccard similarity. It's not covered here, but you can find implementations online. So string-based hash functions, min hash, actually just work on set-based hash functions. But now we need to hash signatures. These are strings, not sets. If two strings have the same symbols at many corresponding positions, we say they are very likely to be in the same buckets, right? Remember, when we look at two strings, we say these two strings are similar if many of their corresponding locations have the same value. So if many of their corresponding locations have the same values, we say they are in the same buckets because they could be very similar and we want to compare them. If not, if this is not true, then we don't want to compare them, right? So can we find such a hash function to help us do this? All right, so our idea is to determine the buckets for a signature so that we can compare some portion of the signatures without looking at every signature. We compare the signature symbols with the corresponding signature for the signatures in the buckets, amount to compute all pairwise signature similarity, and that's not good. That means we want, well, this is really, so there's a question, are we trying to min hash a string because we are trying to hash the min hash of the set? Okay, we are not trying to min hash a string. I show you that we cannot min hash a string because it requires the card similarity. So now we are trying to figure out a way to look at two strings and to be able to determine if these two strings are in a similar bucket. If they are in a similar buckets, we say we want to compare their similarity because they are. Let me show you guys on the whiteboard. Okay, so this is our S1 median minus 1. Oh, we don't have to minus 1 because we start from 1. S1 median, dimension 0 to dimension 10 median minus 1. I call this dimension, but this could be shingles, right? But very important thing to remember is the min hash that we covered in class is using this 0 and 1. Okay, so you can only have zeros and ones. And we say this is too big. We don't want 0 and 1s. So instead, we use these min hash functions and all these really cool permutations to help us create signature, M signature 1, M signature 2, and maybe M signature to 100. Okay. So now from 1 and 0 in this table, it becomes 2, 1, 3, 4, something, some locations. So we solved one problem. We solved the problem that the dimension is too big. But the other problem we haven't solved is you have 1 million documents you have to compare. So we are saying now let's compare these two. But before we compare them, we want to know if we have to compare them, right? It's very similar to this PCY idea or a priori idea. Before you count it, you want to know, do you really need to count it? If the probability of these two signature sets, signature strings to be similar are low, we don't want to count. We don't want to compare them. Let me repeat this again. You always have a target goal. You will say, I want to find the document has at least 80% similarity based on your card. Okay. So to identify document pairs that have 80% or above job card similarity, we need to compare all the document pairs. But if we have a way to hash buckets, we can say, hey, let's take this one and take the second one, and based on a hash function, let's see if they will be in the same buckets. I haven't tell you about the hash function yet, but let's just assume you have a magic hash function. Let's say this magic magic hash function. Take this and take this, and it says no, they are not in the same buckets. Then you're good. You don't have to compare this two. Then you take the next one, this one. Go back to the magic hash function. Again, it says yes. It's likely they are similar. Larger, their similarity is larger than 80%. You say, okay, then we really compare them. Right? You compare each location. You do this for every pair and you're done. So the real question is, how do we find this hash function, or how do we simulate this hash function? Let's go back to the slides. I hope this is clear. So it's actually very simple. If you don't look at here, just look at here. Instead of comparing two signatures, entire signatures, we just take some samples from the signature and we just compare them, right? So think about this. If you have two signatures that are very similar, their samples should be similar as well. So this is very similar to this idea of sampling in the limited path algorithm in frequent item discovery. That's it. This is the entire LSH algorithm. But exactly how do we take samples, and why is simple? What? And so exactly how we take samples and are different strategies of taking samples important? Let's look at this. So we say if two signatures are similar, their samples should be similar. By taking samples, we can divide the each signature into small bands. Then for each band, we just use a hash function to hash them individually. We will only consider pairs, consider to compare two strings if they hash into the same bucket in at least one band. Okay, so this is important. Such pairs are called candidate pairs, which means they could be similar, so we want to compare them. So this hash function is a unique hash function that only identical strings will be in the same bucket. So for example, let's look at here. Let's say in your entire, this is all your documents, and this is their signature strings. We have 12 signatures for each document. We can divide them into 4 bands. So each band will have 3 signatures, right? So if you look at the sample here, it has 1, 3, 0, 0, 2, 1, 0, 1, 3, 0, 2, 1, 2, 2, 1. Okay. On the slide and in the textbook, it tells you that, hey, let's just take this 130 hash, use a hash function, hash into some buckets, and take this 0 to 1 and hash into another bucket, and do this again for everything, which can be confusing. But the real thing is you just take this 130 and you compare it to 0 to 1, and you say, are they identical? If they are not identical, they will not in the same bucket, okay? And looks like you don't have any pairs are identical here, so none of them will be in the same bucket. So 2 vectors hash into the same buckets if and only if they are identical, right? Like I said on the last slides. This requires symbol by symbol comparison. For example, column 0, 2, 1 and 0, 2, 1 has to be the same. 2 signatures are candidate pairs as long as they agree on all rows in at least one band. Very important. Let's come back to look at this on the whiteboard. All right, so our input for the LSH is here, right? And our goal is to determine if we need to compare two strings. So it's very simple. We just take this string table, S1 to S1 median, this 1 million documents. This is their min hash signature 1 to maybe min hash signature 100. I'll just tell you how we would implement this. So the idea is to, if you look at two documents and you say, should I compare them because I want to find documents with 80% similarity. And I want to avoid compare every row in this table. So what we can do is we can slice the entire table, let's say into 3 parts, okay? I call this band 1, band 2, and band 3. Okay, when you implement it, and also in the algorithm, you will choose a hash function. You will say I have a LSH hash function 1, LS hash 2, LSH 3. Okay, so if I tell you, remember we say always ask about input, process, and output. The input for the hash function is a string of size R. And what is R? R is the number of rows in a band. Okay, so that's the input to your function. And what is the output? The output is a bucket number. So bucket number. Okay. And very important is this bucket number is unique. That means every string will have a unique bucket number. 0 to 1 will have a number, 0, 1, 2 will have number, but if you come back as 0 to 1 again, it will have the same number of 0 to 1. Okay, there's no collision. This is very important. No collision. No collision. And you do the same for this one and this one. Okay, it's just they are not the same hash function, but the property is the same. The input is a string of size R, and the output is the number of buckets, and there's no collision. And what's really nice about this is now you don't have strings anymore. You don't have really long strings anymore. Instead, you have what? You have 1 number, 2 number, 3 numbers for S1. So for example, the bucket number for this string could be 2, S1, 30, and for this one you can have 2, 2, 3. This one you can have 1, 1 to 100, 4, and so on. Okay, and when we look at two strings, when you look at string pairs, we say, oh, you have 2 and 2. That means what? That means this, all these R corresponding rows here are the same because LSH1 function do not have collision. They have to be exactly the same. So you say, all right, they are the same, so we have to compare them because a big part of one of the sample are identical. We have to compare them. And when you are looking at, let's say, S1 and S3, you say 2, 1, yeah, not the same. 1, 100, not the same. 30 and 4, not the same, so we don't have to compare them. You don't have to go back to the original signature. Now you only compare how many times? 3 times. If you are looking at this 2, you say 2, 1, no. 2, 100, no. 3, 4, no. We don't have to compare them. Great. So they're not in the same bucket. Okay, all right, good. This is the entire algorithm of LSH. But the next question becomes, hey, you're taking samples, so there's there should be all these false negatives and false positives, right? How do we evaluate this? How do we know what is your B? Oh, sorry. How do we know what would be a good number of B? How many bands do you need? How many, what would be the size of R? Well, we know that R times B is the total number of rows here, but how do you decide? And is there any implications about their sizes and your false positive and false negatives? There's a question, should we use different hash functions for each bucket and why? Let me think. No, you don't. You can use the same hash functions because you're only comparing if two strings are the same. All right, so let's take a 10 minutes break. Come back at 7. If you have any questions, feel free to leave in the chat. I will answer them when I come back. All right, I'm back. So question, is it possible to sample rows in min hash also? If not, it's possible. If not, is it still efficient when there's millions of rows? That's a very good question. So think about dimension reduction. We're going to cover some of the dimension reduction in your clustering algorithm. So we're talking about medians of in your min hash. Your sets is really large, right? It can have millions of dimensions. And your question here is instead of scanning this really large table, can we sample the table and have some similar result? Yes, you can, but your sampling is a random sample. So you don't know if you're going to miss some important rows. And you cannot guarantee the same Jaccard similarity equal to this signature, the same property. So yes, you can sample it, but I don't think the result will be the same. So you don't want to sample it in summary, because you only scan the entire table once. If you want to sample it, you still need to scan the entire table, right? All right, so we talk about min hash, and talk about this, and I think we were. Okay, so remember when we were working on this problem on the whiteboard, we talked about if two bands are the same, we want to compare them. That means when two bands are the same, these two signatures becomes a candidate pair. And let's look at the probability of them become a candidate pair. The probability of min hash signatures of X and Y agree on any row of the signature matrix is S because of the Jaccard similarity is S, right? Are we good? Anybody? If we have two documents, X and Y, their Jaccard similarity equal to S. So we know that their min hash signature agree on any row of the signature matrix is S. That's the probability of hash X equal to min hash Y, right? What is this probability? This is the Jaccard similarity of X and Y. If you still are not sure, let's look at this. We are actually talking about the probability of this equal to this is the Jaccard similarity between S1 and S2. Okay, the probability of this equal to this is the probability of, is the Jaccard similarity between S1 and S2, which is there, somewhere there, which is here. Okay, so we showed this last time. So why is this important? Well, let's look at this LSH. Go back to. If we agree on this, now let's look at what is the probability of two signatures become a candidate pair. So signatures are divided into B bands, R rows per band, right? Exactly like what we did on the whiteboard. What is the probability of two signatures agree on all rows in at least one band? Well, we can calculate this probability based on S. Let's look at how we calculate. So our question is the probability, we want to find the probability that two signatures agree on all rows in at least one band. This property make them become a candidate pair. And we need to consider many cases, right? Signatures agree on band 1, or agree on band 2, or maybe band 1 and band 2, or different types of different combinations, right? So whenever we need to consider many cases, we will just take the complemental probability first. So what's the complemental probability? Your P prime is the probability that the two signatures disagree on at least one row in all bands. That means you don't have to compare them. They're not candidates. So your final probability will be P equal to 1 minus P prime. Are we good? Okay, very simple. This is just definition of the terminology. So let's look at how we calculate P prime. P prime is the probability that they disagree on at least one row in all bands. The Q is the probability that they disagree in at least one row in a band. So P prime is Q to the power of B, right? Because you have B bands. B prime again, they disagree on at least one row here for all bands, right? And we have a new term. This is this disagree in at least one row in one band. For all band is Q power of P. Great. The probability of all rows in a band agree is S to the power of R. Why? Well, because the probability of one row agree is S, right? That's our Jacquard similarity. And now in a band, you have R rows. So all rows agree is S to the power of R. So think about if your Jacquard similarity is 0.8 and you have two signatures in that band, R equal to 2. Then for this first one to be the same and the second one to be the same, it's 0.8 times 0.8, and it's S to the power of R, and S is 0.8, R is 2. So R is the number of rows in a band. If you have this, if you understand this, Q will be 1 minus S to the power of R, right? So because this is all rows in a band agrees, and your Q is they disagree in at least one row. So it's complemental probability again. So now you have the Q, you know that your P will be 1 minus, what is this? This is your Q. What is this? This is Q to the power of B, that's your P prime, right? Your complemental probability. The probability, this is the probability that the two signature strings disagree on at least one row in all band. So the probability of them being a candidate pair, we'll take the complement. There you have this. Let's look at some examples. The probability of agreeing on all rows of a band is S to the power of R. So this is agreeing on all rows in a band. The probability of disagreeing on at least one row of a band is 1 minus S to the power of R. It could be this, right? At least one. It doesn't have to be one. It can be two. Probability of a disagreeing on at least one row in all bands, and you have B bands. So this to the power of B. The probability of agreeing on all rows in at least one band is this. All right, so great. We have the probability function of two signatures become a candidate, so that we have to compare them based on three values, based on S, based on R, and based on B. Cool. So if we plot them, this is your S, Jacquard similarity between two documents. This is their candidate probability of becoming a candidate. This will be your function. And if we set B equal to 20, R equal to 5, you will have a curve like this. Okay. if you set b equal to 1, r equal to 1, of course, you cannot have these two settings for the same signature sets because your total number of signatures is 20 times 5, it's 100. And here you only have 1, right? But this is just to show you that to compare them, if you only have only one single rows, one signature, your Jaccard similarity is always the same as the probability of becoming a candidate because R is what, 1, B is 1. So 1 minus 1 minus S will be this, P will equal to S, right? That's this line. Okay, but if you have P equal to 20, R equal to 5, you have this curve. So why is this curve important? Well, now we can look at the relationships between the curve shape and errors. So what do we mean by errors? Well, it could be both positives and negatives. And let's look at some definitions of them. Then next time on Wednesday, we're going to look at how curve changes their shapes if we varies B and R. So let's look at B and R first. Say for B equal to 20, R equal to 5, at S equal to 0.8. Do the math. And this means for two documents with 80% Jaccard similarity, 33% chance they will agree in all 5 rows, right? R equal to 5. 1 in 3,000 pairs will fail to become a candidate pair. That's this probability of becoming a candidate pair. What does this mean then? Well, this means, say if our similarity measurement is 80%, okay? We want to have all the documents that are 80% similar. Then we use R equal to 5, B equal to 20. Will all documents that have 80% similarity become a candidate? No. You still have a small chance that some documents will not become a candidate pair. And if you look at this table, it tells you that from your Jaccard similarity to 0.2 to 0.8, what are their chances of becoming a candidate? And you can see pretty clearly here that if you have a 0.8% similarity, your chances of being a candidate pairs are really high, okay? If you only have 0.2, your chances are pretty low. So let's just assume in our application, we are setting a threshold of 0.5. We say we want everything that 0.5 has a higher of 0.5 similarity in Jaccard similarity. Is this a good setting? Anybody? Let me ask the question again. Our setting is only look at B and R, right? We cannot change S. S is your document similarity. And we can also have one setting that's about your application. And I say for my application, I want to find every document pair that has an over 0.5 Jaccard similarity. Okay, so 0.5, I really care about 0.5. And I use I use B equal to 20, R equal to 5, and this is my candidate probability. Is this good? Well, this is not particularly a good setting because when you are looking at this number, that means assuming that I have 1,000 pairs that has a 0.5% Jaccard similarity. I want to compare them, right? I want to find them. However, the probability that they will be in the buckets so that they are a candidate pair, I will really compare them, is only 0.47. That means there will be 470 pairs that I will compare, but for the other 503 and 30 pairs, I will not compare them because based on this setting, they are not even the candidate pair. So I will not compare them and I will lose them. So these are your false negatives, right? You say they are negatives, we don't need to compare them, but you actually want them because your similarity threshold is pretty low. However, if I have my application demands a much higher similarity threshold, say I only want to find the document with the Jakarta similarity larger than 0.8, then this number is pretty good. So for everything that has a 0.8 similarity, the chances that they will be in the same bucket so that I need to compare them is really high. Only 1 in 3,000 pairs will fail to become a candidate pair. All right, that's it for today. Any questions? So yes, there's a question. So the 1 in 3,000 chances it fails to identify candidates, the chances that all 5 bands do not have a single row. Yes, you are correct. It means all bands disagree. Okay, guys, it's quiz time. So still have 1 minute. You can go to Blackboard and download your quiz. And today, the quiz is not easy. So I shouldn't say not easy. It's not very difficult as well. It's take time. So I'll give you 10 extra minutes. You can work until 8 p.m. Please do turn on your camera. If you don't turn on your camera, we're going to give you, I think, I don't remember the penalty, but your grader will give you some penalty. Camera, we still have some people.
Yai, I think one student has question on chat. So
Is there still a 5 minutes buffer? Yeah, there is a 5-minute buffer. Camera, please. Oh, well, not just turn on your camera. We need to see you. Okay, back. And mute yourself, please.
If you were not expecting this call, thank you. Goodbye.
There is a question in chat about the first question. The students say, why is I plus j plus k? From my understanding, it's just a way to define the hash function. So I'm not sure. Hash pairs. I think if in this way, so yeah, it's triple instead of pairs. I think so. Let me double check with the instructor. So the question says to find the frequent pairs. I think it's only use the hash function including k, but the answer is still, the solution is still to find the frequent pairs. Let me know if you have any more questions about it. Yeah, you just make a clarification. There's no k, so the hash function is only I plus j mod 6. Seems like there is no questions 3. So let me double check with Yao Yi and you can continue with other questions. I checked with Yao Yi, so just as an ordering problem, we don't have question 3 here. So totally we have 5 questions.
Hello, Wei Wei.
Hi. Is any questions?
Yeah, can you explain a little bit about the memory footprints?
Which question?
Question 5, because I don't quite understand what is memory footprints would be like.
Let me take a look. Hmm. I think it's the changes of the main memory. So the green box means the main memory, so how it changed over the process.
So should we just draw a picture referencing the photo?
Yeah, I think in the lecture you have similar.
Yeah, I got it. Thank you.
Mhm. I don't think you can have extra time for the hash function confusion because Yoi didn't tell me you would have extra time for it. So it's time up, and you can use the 5 minutes buffer to upload your answers. And if you have any networking issues about the camera open, you can explain your situation to Yoi by email. Thank you.